Okay, so what I wanted to do is to give you a quick how to say, overview and guidance on how to think about the exercises this week. And what I will focus on is the bias-variance trade-off. Now, in one of the exercises, and one of the reasons why I will be a little bit, how to say, slow going here, hopefully, is that many of you may not have had a coherent course in statistics. And if you look at this course here, it's actually a course which brings in the statistics and the mathematics you basically have had in a bachelor's degree. And a small hint as well, if you go back to the exercises of week 35, which you obviously have access to in the lecture note, there is a link to a textbook by Faisal et al., which is called The Mathematics of Deep Learning. You use chapter 5 for solving the exercises in week 35 with derivatives of matrices and vectors. But there is also chapter 6, which in a way brings back and synthesizes the statistics which you need in machine learning. So that book is at an excellent level towards the end of a bachelor degree and beginning of a master degree, which is roughly where most of you guys are. So hopefully, if you want to brush up your statistics and linear algebra, etc. knowledge, that textbook may be helpful. Now, in the exercise, you're asked to find the expression for the variance and the bias. And the question is, why do we do that? Now, because the bias and the variance, hopefully, they can give you a deeper insight of what happens when you're overfitting and also underfitting. The exercises which you have asks you to derive an equation for the variance and the bias. And in the bias, when you set up the equation, what you will see is that there is no y here, which are the data, but there is the unknown function f. So some of you have probably arrived at that equation, but not with y. And you can see now down in the exercise, we added that when you want to actually evaluate it, since we don't know the function f, we replace f with what we know, the output data. So that is from a practical point of view, if you want to be able to compute something. Now, let's look a little bit at the things which we picked up during the lecture. So I'm going to go back to the whiteboard a little bit, and I wanted to show you how you reach that equation for the bias and the variance. Now, if you look at the typical thing which we end up doing when we run a machine learning method is that you will typically plot, if you're doing a regression case like this, where you're fitting a function, you would plot the mean squared error on the test data. That is the thing which is of interest, because then you're applying it to data which has not been included in the training. And it's pretty obvious for most of us that you can train to perfection, but then there will be data points which were not included in the training where you can fail miserably. Now, one of the reasons why you do the resampling technique is that you want to calculate a mean squared error, which is an expectation value of the sample of values you have. So we call that a sample mean. You want to calculate that in the most reliable way. So one way, obviously, is to generate new data continuously, which you can do in project 1 and the exercises here, because you have simple functions. That means you can calculate one mean squared error with a data set. You generate a new data set, you compute a new one, and then you do this many times, let's say 100 times, and you take the average of the values. So when you run it on a data set, you may get something like the lower red line here, and then you get something like the upper one. But then when you do this many times, you can then take the average. And this is the average. Hopefully then it will have a smaller standard deviation in the values of the mean squared error. And we discussed that during the lecture when we showed how to use the bootstrap method to generate new data and then we approach the central limit theorem, giving us a smaller standard deviation. So when you make a prediction and you want to present a model, you want to be pretty confident that the error or the mean squared error you're presenting is something which is the best you can achieve, okay? So this is much of the philosophy behind resampling methods. Now, the typical thing which you do is to then plot the mean squared error on test, and then you would typically say that where it hits a minimum, that's where I have the optimal parameters for this data set. Then you're done. Now, what we want to do with the bias-variance trade-off is actually to develop a deeper insight about what is going on. That's the essence of the bias-variance trade-off. Normally, as a practitioner of machine learning methods, you don't do the bias-variance trade-off analysis because you already have this insight and you know what is going on when you overfit or underfit. But we are going to bake it in the project simply because we want you to think a little bit more carefully about the data, and then you have a tool to analyze what is going on in terms of the deviations from the output value you want to reproduce and the variance of the model itself. And then you can split up the data in the bias and the variance and have an analysis which would then match with where you find this optimal point. So that's the kind of overarching goal of what we are doing. Okay? And but as I said, in project 2 and project 3, unless we ask for it, you won't do it because that requires additional numerical evaluations. And the main message is actually what you see here. And that is this figure 2.11 of Hasty, which you also try to reproduce in the weekly exercises in week 36. But let's now look at the bias-variance trade-off and just go a little bit through the mathematics. Now, we are calculating the mean squared error, which you see here. So this is one way to test the quality of our model. And we write this as an expectation value because this is a sample mean value of the square differences. And you would typically see it written like this. Some of you may have seen this notation, which often appears more in quantum chemistry and physics. But I will use the standard mathematical expression for an expectation value. And this is the sample expectation value. We don't know the true probability behind the Ys. And that means that what we will calculate may not be the true value. So the true value is something which, suppose now we just write this out, we would have the first term, we have this expectation value and this expectation value. So the exercise which we have this week is simply us analyzing these different terms and rewriting this expression here in terms of 3 different expressions, which will allow us to analyze the data at a deeper level than just that simple image or figure which you saw previously. Now, if we have the probability distribution which governs the generation of these points, then we can calculate the exact expectation value. Now, when we calculate the sample mean for this one, which then will just be a sum over all the n observations we have, we may not get the exact value. Now, the problem we face in essentially all applications is that we have no idea, or if we have some idea, we don't have a nice mathematical expression for the probability. Okay, so when we do machine learnings normally, we would like to have this, but we hide it under the rug and say that, okay, I'm just going to compute the sample mean and hope for the best. So one of the reasons why you also do these resampling methods is that if you have few data, you want to generate more data in a cheap way. And the bootstrap method is one of these. So just to give an example, which we use in the lectures, there was a survey in the UK which went over 30 years with 500,000 people, which they followed for 30 years in order to see which kind of mechanisms could affect cardiac diseases. But you did this for 30 years. And it's very unlikely that you will be able to do it another time for 30 years. So the data you have then, this 500,000 persons, which they observed for 30 years, that's the data you have. And then the statistical analysis you're going to do then will be based on that data. So an example from my own research, I deal often with the strong force in particle physics and nuclear physics. And when I run calculations, sometimes they can run for a month, and it produces something like 1,000 observation points or points. And 1,000 is not much in order to run a statistical analysis. So that's why you often use some of these cheaper methods like the bootstrap. Now, if you look at the expressions, let us now just break this down, because this is what you're going to do in the exercise here. So as I said, we are recording this session, and you will also find this under the handwritten notes for this week. Now, if you look at the first term, now the second term, this one, actually it's the third term. I cannot count anymore. So it's this term here. This is something which I can write out as the variance plus the mean value squared. Because the variance of a given object is given as the expectation value of x squared minus the mean value. So what I'm doing now is simply to write out one of these terms in the mean squared error in terms of the variance of the model. So that it's going to tell me how much my predictions are scattered from the mean value of the model. So if I have a big scatter, then what happens is that I will often end up in a region where I overfit. And we will see that in practical examples. So now we already have the variance, but we have something else which we need to take care of. Then let's look at this term, which is the first term when we write it out. Now, what we are doing now is to bake in the basic assumption we have made about the data set. And this is, it does not need to be the case, but what we are making is an assumption about y to be given by a function which is non-stochastic. So you could think of an example where you are going to input, let's say, the velocity of an object, and then you're studying how this evolves over time. So it means that when you look at your input, you're thinking of that as a non-stochastic variable because you fix the velocity. So you would then say that the velocity is well determined from the beginning. And then you look at how the system evolves as a function of velocity. So that's why we often make an ansatz where this function f of x is a non-stochastic function, which is then not governed by the probability distribution which governs y and epsilon. Does that sound reasonable? So if you're running an experiment, you can actually say that I can fix my input precisely. And we are making an assumption that the data can be described by a continuous non-stochastic function. So this could be a sine or cosine of something, just to give an example. Then there is a random noise, which becomes a parameter. And that random noise has a mean value 0 and some variance, which we may not know, or you would typically fix it. So in the analysis of the bias-variance trade-off, we normally leave out this term here, because this is just a parameter which we would typically fix, unless somebody tells you that your data follows that specific standard deviation for the noise. Hey, feel free to sit down here, eh? Come on. Please. Okay. So what you do then is to take these terms and just write them out. So that means that we have one expectation value here, and one here which we need to evaluate. So when you do that, is it okay if I just shift? So when you do that, what we have to think of now is the following. So if I look at the expectation value of f, I said this is a non-stochastic function. So in principle, there is a probability distribution which governs y and epsilon. And that would be this guy. Now, f of x is not affected by this one. So that means that we could put f of x outside, and simply, since the probability is normalized to 1, then this integral becomes 1, and we are left with f of x. So in statistics, this is often called an unbiased expectation value, where the expectation value of the function is equal to the function itself. Now, there may be a probability distribution which governs x, but we don't know that. So if there is one, the mean value for f of x may not be equal to the one we put up here, but we don't know that. And in our case, we are saying that this is a non-stochastic variable. Then, if I look at the next term in that expression, then what I have is that f is not affected by the distribution of epsilon. So we can put it outside, and we have defined the mean value of epsilon to be 0. So that means that the term with the expectation value f times epsilon is equal to 0. So this expectation value of y squared is simply equal to the function value squared plus this standard deviation, which variance, which we have defined as a parameter in the model. So that's the first term which we have looked at. So we have done this one, we have done that one, and now we simply need to do that one. So if I do that, we now look at this term. It's actually -2 times that term. Then what we have to evaluate is this function, f plus epsilon times y. Now here we have f, so if we now assume that there is a probability distribution behind the model, that does not act in the space of f of x. So the assumption we are making then is that we can pull this outside as a constant, and then we simply have the expectation value of y tilde. So these are again assumptions we are making about the data set. Then this guy here, what we typically assume now is that these are independent variables. What does that mean? If you think of a probability for x and y, when they are independent, that means that you can use the product rule and write in terms of a probability P1, which governs only x, the generation of x, and P2, which governs the generation of y. This is a standard product rule for independent stochastic events. Now, if you have independent stochastic events, then this is what you would calculate. And this separates out in one integral for x and one integral over y. So this term, which you see here, becomes an expectation value of epsilon and an expectation value of y. So we've made an assumption about the data here. And if you use that assumption, then this term here, this one, epsilon, this is exactly equal to 0 because we define the mean value to be 0. And then you're simply left with 0 here. So this term here simplifies simply to that one. Then we can bring everything together. So when we then bring everything together, we have this f squared -2 times f times this expectation value. We have this one because we rewrote y squared tilde in terms of the variance plus the mean value. Then we have the variance. And then we have this variance, which is just a parameter, which we normally leave out when we do the bias-variance trade-off analysis. So we can then rewrite this term here. As you can see, this is nothing but this expression squared, f minus the mean value, So this is what we call here is what we call the bias. And this is the variance of the model. And this is the standard, or the variance of the noise which we have. So this is nothing but a rewrite. These terms which you see here are nothing but a rewrite of the original mean squared error. So this is essentially the kind of analysis which we are going to do now when we want to understand at a little bit deeper level what is going on. So if you look at the expression, this is the formal mathematics. But since you don't know f, because if we knew f, there is no point in doing what we're doing, because we have an exact function which describes the data. So what we do then, we cheat a little bit. And it's always stressful for those of you who come more from a mathematical study direction, because then you say, why? I mean, you should keep this expression, but we need to plug in something in order to be able to calculate. So what we do then is that we replace f with the output data. But in principle, this is the expression, but then we need to do something in actual calculations, and then we make a simple approximation that f is then approximated. So what we do then is simply that we approximate f with y here. Okay, so I wanted to go back to some of the things we have in the lecture notes for this week. So let me just do that. So we have now split everything. So this is, in principle, we should put an approximation sign here, because you should have f. But if you can live with the approximation, then we can then proceed. So the kind of thing which we are doing now is to try to build up some kind of intuition about what goes wrong. So the bias-variance trade-off is a way to analyze the data. Now, if you look back at the example which we discussed during the lectures, if you now think of the point here, this is the y value, your target. That's what you want to reproduce. Now, the blue dots here, they are then the predictions you make with a model. Okay? Now, what you see here is that you have a big scatter in the predictions. So if you have a big scatter in the predictions for the model, it could happen now that the mean value of the model, if the mean value of the model is here, which seems plausible, if you then go back to the variance, what it means then, this quantity here, you will have a big variance. So when you have such a big scatter here, it means that you will end up in a region where you're overfitting. So this is on the test data. So your model makes a prediction on the test data, but where you have a big variation in the mean value of the predictions to the test data, and you have this big variation which simply means that you have a high variance. If the prediction you make is close to the mean value, so the different predictions, then you will have a small scatter, and you will then see that this leads to a case where you don't have overfitting. Now, the ideal one is obviously if you have a low bias and low variance. So if the mean value of your data is here, close to the middle, that means that this bias which you calculate, this quantity here, is small. So low bias is wanted and low variance. Now, if we think of this as you being at a shooting range, so we stay with this more violent example, and you're shooting on a target, and your result looks like this. This is a case where you will have a low variance, a low spread, because if your mean value is then concentrated near these points, then you will have a low variance. Now, this is an easy case to fix, because if you, I don't know how familiar you are with I say it's a violent example with rifles. The thing you would do then is just to fix on your rifle the aim, sikte. That's the only thing you need to do, because your training is pretty good. I mean, your training tells you that you are, as a person who manages this rifle, you're actually able to center all your aims in a small region. So the only thing here now is probably a defect with your rifle. So that's something you can fix. In this case, high variance and high bias, you need to train more, because that tells you that as somebody who manages the rifle, you're not doing too well. So you need to train more so that your end result is actually here. So training more means that the model you have cooked up is something which needs improvements, and you need to have more data and train better. This case also is an example of a model which is not good enough, but you can fix it on a rifle by fixing the aim. Okay, you see the parallels? Even if I bring up a less friendly example. If we now go to the Jupyter notebook, there is an example code which we looked at the lecture. And in this case, what we are going to do now is simply to break things down in terms of a bias and a variance, and we compare that with the mean squared error. So in this case, it's the same function which you have seen tons of times. So I'm just reusing the same one. My wife and my daughter would claim that this is due to my lack of fantasy, that I just repeat the same things. But it's a nice example. And it's also a test case which does pretty well to illustrate things. We train and test, test split the data before we start doing a bootstrap. I have 40 data points. Normally, there is no kind of convention on how many bootstrap you should use. So here I'm just making 100 new samples of these 40 data sets using the same 40 numbers. Many practitioners have less bootstraps than data. So I calculate then, I do the model prediction for a polynomial degree in here by resampling. So every bootstrap here is me fitting a model, but pay attention that the test data is kept the same, because else you will be comparing apples with bananas if you do a train test split every time you do a bootstrap. So the test data is something you have to think of, something which is untouched by the training process. You keep it in a safe, and then you bring it back when you're comparing the model with the test data. So here I'm making a new data by resampling. So this is a function which does the bootstrapping for you in scikit-learn. Feel free to use that. There is no need to write your own. I had an example of that in the lecture when we looked at the normal distribution. And then I make a prediction. And you see now the test data is always the same. It just kept fixed. And then I compute my error, my mean squared error. I do the bias and the variance by plugging in those expressions, which you saw previously. And then I plot them. And what you would get then is actually something like this. So I've been tuning the data set to get something which looks like what you see in the book of Hasty. Now, if you look at this, you have a very small variance in the beginning. So that means you have a situation, if we go back in the very beginning, where we are here. So the model is very simple, and often with a simple model, you tend to have a small variance. But then your bias is high because you have a poor model. It's as simple as that. And you see now the bias is essentially the one which dominates the mean squared error. And this follows simply from the fact that you have a simple model. So your prediction then, your mean value of your predictions on the test data is actually not that good. Now, that sounds reasonable, right? I have a pretty bad model. Then you see now that when you increase the complexity of the model, you're getting a test mean squared error, which is becoming smaller. But then at a certain point, the variance starts going up. So what you're doing, where you're ending now is in a case of overfitting. And overfitting is then simply reflected, if you go back to this figure, by something like this. So we have a small bias still in that example. So the mean value is not so far away from the data set, but then the variance is getting higher simply because we are entering a region of overfitting. And in all practical calculations in this course, after project 1, you will normally just plot the mean squared error on the test data. And then you will say that a polynomial of degree 8 seems to be giving us a pretty good result. So in project 1, you will make a recommendations based on the training you have done. And you would then say that for this specific data I have, this is the best model I can give you. So that would be a typical conclusion which you would present in project 1. So clearly beyond polynomial degree 8, you would then say that I'm entering a region of overfitting. Now you can go back and you can have more data. So that means that your training is getting better. And if you do 80% here, it means that you have only 80 points which enter the test case. So you have 320 points which are used for training. So hopefully then if you run the case now, you may see something which looks better for a polynomial of up to degree 13. And now what you see is essentially that the variance is extremely low. The bias follows essentially the mean squared error. And the bias is essentially the mean squared error when you reach a certain model complexity. So this is a typical case of low bias and low variance. And that's the ideal. Now, you, as a person who trains a specific model, when you're making a recommendation now, you would say, if this is a polynomial fit, you would say that anyone who's going to use these results, a polynomial degree of degree 8 does a good job. A good enough job if you're happy with this error. So at the end, it's you who decides what is the best model. So one of the things we want you throughout the semester here is actually to develop this kind of a practitioner spirit, where you at the end can say that this is the best model we can get with these and these algorithms. Take it or leave it. So there is no point if you do a polynomial fit to give somebody a polynomial of degree 12, because that requires many more floating point operations if you're going to implement that in another code. So typically this fit is something you would use in another application. And clearly then you want something which is fast to use. Okay, any questions, guys? Did this help a little bit more? Yeah, go ahead. Yeah. Oh, yeah. No, so these notes will be, if you go to the handwritten notes for this week, I'm going to upload these notes. So the notes you saw, the handwritten ones, the lecture notes, you have them. But if you go to the, so every week, what I do is actually to put in the notes from the lecture notes, from the lectures, sorry. If you go to handwritten notes, that's what I call them. And you go to 25, and then this is going to be updated with the notes you saw now on the calculation of the bias-variance trade-off. So, yeah, that is from Monday, but now I'm going to add to that one what we did now. And then you will also see the video, so you can always revisit the video. Because the thing which we find every year is that you guys are, from the beginning, a heterogeneous group. That means we have people from mathematics who have done lots of statistics. We have people from bioscience and physics who have less statistics. So you guys being a heterogeneous groups means that sometimes it takes a little bit more time to repeat some of the things and to put them in the right context. So think of this course as a course where you use the mathematics you've been having in your bachelor degrees, and similarly, the statistics, which unfortunately in many bachelor degrees is scattered throughout many different courses. That is I would say, an unlucky situation which we are trying to compensate for with the own statistics courses. So the statistical data analysis is something which is always under the surface when you do machine learning. And in this course, we put them in here and there when we need them. So the Faisal text, which you have in the lecture notes for week 35. So let me just bring that back so you can see that. That's a very useful text, actually. So if you go to week 35, the lecture notes then, because then we looked at the derivatives of matrices and vectors and so on. This textbook here, in that specific week, we looked at chapter 5, but chapter 6 has a very nice discussion of the statistics you need for machine learning. And the title of the book is actually Mathematics of Machine Learning. So it has all the kind of pretty small details which we often have forgotten about when we come to this course. You studied these things 1 or 2 or 3 years ago, and we are humans, so we tend to forget. So that book is actually pretty nice just to look up if you want to. I think Carl Henrik has something he wants to say as well.
Yes. This week's exercise, week 38, exercise 4A. So on the line that says targets, be a product of ground. And now, bootstraps.